Section 2.7 is called Implicit Differentiation. We have not done anything that was implicit yet. So implicit, you might think of another word, another English word that means the same thing might be like inferred. It's this sort of thing that's not exactly stated, but you're sort of trying to figure it out from behind the scenes. And that's exactly what this actually means in the context here as well. We've done the first one. We've done explicit. We didn't call it that, but that's what we've done, is explicit derivatives. So what is explicit derivatives? Well, it's taking a derivative where you've got y on one side, and you've got all the x's on the other side, or if it doesn't look like that, you could change it to look like that in that form. And then you actually take the derivative from that perspective. That's exactly what we've done on every problem so far. Y is on the left, or f of x is on the left, or g of x is on the left. But then the function on the right-hand side has only x as a variable involved. That's explicit differentiation. Okay, everybody good so far? Okay, let's take a look at what implicit then means. Implicit means taking a derivative of y in terms of x when you either cannot separate y is on left, x is on right, or maybe you can, but it's easier not to. Okay, so in order to use this method, we have to treat both x and y as variables, and then we use all the derivative rules we've learned so far. So every time I see x, I'm going to treat x like I always have. The catch is that when I see y, I'm going to treat it differently than I have before. It's going to look a little different because it's not going to be all alone by itself. It's going to be multiplied by an x or divided by an x cubed or something like that. And so we're going to have to treat it differently because it's involved in the differentiation. All right, so an example is in order because none of that probably made a lot of sense at this point until you see one in action. All right, take a look at this example. This is an example where we actually could solve this for y equals. I mean, right, we would subtract the 37, we would divide by x squared, and then we would take a square root. We could do all that, right? Yeah, I mean, we could actually solve this one for x. It would make it awfully complicated. It would turn it into having a quotient. It would have a square root around it, which would be a chain rule as well. So we have a chain rule and a quotient rule inside of my problem. And we'd also have a plus or minus because I took a square root. And when I take a square root, I have to put a plus or minus involved. That's not real friendly. So I'm going to show you an alternate way of doing that, and that's with implicit differentiation. So here's what we're going to do. We're going to look at this, and this says x squared times y squared. So when we have two functions that are multiplied and they both have a variable in it, that's something we use the product rule for. All right, great. So this is a product. I have this piece and I have this piece. So far, so good? Product rule? All right. Product rule says that I'm going to take a derivative of one piece and leave the other piece the same. So which piece do you want to do first? What do you want to do? Tell me what to write down. 2x. 2x. All right. And then y squared. Okay, so that's taking the derivative of the first piece and writing the second piece down. And then I use addition, right, Josh? Yeah. And now I need to do the opposite. So now what do I write? Okay, I'm going to write the x squared first because we're going to talk a little bit more about that 2y. It is going to be an x squared. It is going to be a 2y. But there's a catch. Here's the catch. Y is actually a function of x. So when I take the derivative of y squared, y actually is a chain rule in and of itself. Think about this when we normally do this. We have y equals all this stuff over here. What's the derivative of y? What do you normally write down on the left when I take the derivative? What's my next step look like? Y prime, right? The derivative of y is y prime. Well, how does that play into my y squared? Well, the derivative of the squaring of something is bring the 2 down, rewrite. But the derivative of y itself is y prime. Now, I don't really want to write a y prime. Your book does use this sometimes. But the problem with y prime written right here is that the prime looks an awful lot like a 1. So instead of writing down y prime, I'm going to use the other notation, one of the other notations we discussed, and I'm going to write down dy dx. Okay, so let me reiterate what happened. We took the derivative of something squared. The derivative of something squared is pull down the 2, rewrite the something to the power of 1. We did that. 2y to the power 1. Okay? The problem is that the thing we took the derivative of, y, actually is a function itself. And the derivative of y is dy dx. So we have an extra piece involved that we didn't have before, dy dx. All right? The other pieces of this are a little bit cleaner because there's no more y's involved. What's the derivative of 37? That's 0. I'll write plus 0 just for the moment. What's the derivative of the 4x? 4. Now, this piece right here, the way that this is described, means that they want me to find as my answer y prime equals, or dy dx equals. So the last thing I need to do is I need to solve for this. Okay? So I'm going to solve for the dy dx. Now, the answer that I solve for is going to have x's and y's both in it usually, but I am going to solve for it. So, what would be my first step to solving for dy dx? Fantastic. So my x squared 2y dy dx will stay on the left. And on the right, I will have 4 minus 2xy squared. Now what? Right, so this is the algebra stuff we've been doing before in a different context. We're trying to isolate dy dx, so we divide by x squared 2y, which we could write as 2x squared y if you'd like. The answer then, dy dx, says I have 4 minus 2xy squared over, and I'll pull my 2 in front now, 2x squared y. And this is simplified as far as it says dy dx on one side and it has the value on the other side. But we do want to look and see if the expression that we have on the right-hand side has the ability to simplify any further. And this one does a little bit. What do you notice on the right-hand side? Yeah, all of those terms have a 2 in them, right? A factor of 2. So I have the 4 here, the 2 here, and the 2 here. They're all divisible by 2. So we're going to simplify by reducing them all, by dividing them by 2. So dy dx equals 2 minus x y squared over x squared y. And that's my solution. If you really want to use y primes instead of dy dx, that's okay. Just be careful. Don't lose track of whether it's y or y prime or y to the power of 1 or something like that. That's a little bit notationally difficult. I'm going to do one more problem, and then we're going to pause and put this on hold for the rest of the day, okay? So one more problem, similar question. I am told to find the derivative y prime of x. And in this particular one, unlike the last one, there are 2 y's. You guys see that? And actually, there would not be the ability on this particular one to even solve for y if we so wanted to. On this one, we talked about it being complicated and messy and makes the derivative kind of ugly, but it was doable. Here, not even possible. We would not be able to isolate the y and solve for it. So we absolutely need this rule, this method for doing this that we didn't have before. All right, there are a couple of things to notice, however. The problem as it is currently written has a quotient in it, correct? Definitely does. And we can deal with the quotient rule. That's totally fine. We can do that. However, we could also avoid dealing with the quotient rule if we wanted to. Any idea how we could avoid dealing with the quotient rule on this problem? We could write it as y to the negative 1, which would give me the ability to deal with it as a product. There's another even easier way than that one. Yeah, we could multiply everything by y. And that actually will simplify the problem a lot. So that's my suggestion. Just so you know, that's not what my notes have. I actually deal with it with the quotient rule in my notes. So if you want to check that out with me later, I'll be happy to show you. But we can make it easier. So if we have the ability to make it easier, kind of like with my sine squared plus cosine squared in the last lesson, let's make it easier. Agreed? I have lots of students. I know you guys are probably not near as much like this, but I have lots of students that absolutely hate dealing with fractions. And the reality is, most of the time you can kind of make the fractions go away, at least for a time period, if you want to. And this would be an example of doing that. So I end up with the x plus 3 on the left. On the right, I end up with 4xy plus y cubed. Now, there was an exchange. I exchanged a quotient rule on the left, and I created a product rule on the right. Like, it did not come at no expense to me. You guys see that? I've got a product rule in there right now, don't I? For xy. So I do still have something to deal with, but I don't have to deal with fractions. So it is a simpler problem. Let's take a look at the left-hand side. Let's take some derivatives. What is the derivative of x plus 3? 1. That's nice. The left-hand side's quite nice. Unfortunately, on the right-hand side, we have to deal with the fact that we do have a product rule. So what is the derivative of 4xy? Okay, so be careful. We don't just take the derivative of each piece, right? So if I take the derivative of the 4x and it becomes 4, that's fine. But then what happens to the y? I just rewrite it. Right? Product rule, derivative of one piece at a time. So if I took the derivative of the 4x, I don't take the derivative of y. Now I got to do it in reverse. I'm not going to take the derivative of the 4x. I'm just going to rewrite it. But now I need the derivative of y. What's the derivative of y? That one is just dy dx. Not y dy dx, just dy dx. Okay, product rule results in two pieces separated with addition. Each of the two pieces has the product of one of the derivatives and one of the originals. All right, and then I need the derivative of y cubed. 3y squared, that's part of it, dy dx. Because the derivative of y itself, which is an inside function, that's how we interpret it, is dy dx. It takes practice, I know. And the goal is to solve this for dy dx. Yeah? So everything that doesn't have a dy dx needs to move to the same side of the equation. In this case, I'm going to move it to the left because I've already got a 1 on the left that's over there. Which means what's going to move to the left right now? 4y. The 4y. So I've got 1 minus 4y on the left. And on the right-hand side, everything that's left on the right has dy dx in it, yeah? So what can I do with the dy dx? Pull it out. I can pull it out. Otherwise known as factoring, right, Allison? Yeah. So we're going to factor out the dy dx on the right, which leaves me with 4x plus 3y squared. And of course, on the left, I still have 1 minus 4y. One more step. What do I do? Divide by the 4y plus 3y squared. So dy dx will equal 1 minus 4y over 4x plus 3y squared. And I want to show you something interesting. This is the correct answer, or one of the versions of the correct answer. If you treat this as a quotient rule and you solve it and simplify, this is the solution that I get. I think it was Allison that was in my office the other day that we were chatting and saying, just because your answer doesn't always look like the back doesn't mean it's always wrong. Was it you, Allison? Yeah, okay. And the reason I mentioned this is because I wanted you to see this one. Do those two look alike to you? They don't to me. They're exactly the same thing, mathematically speaking. But I would have to do quite a bit of manipulating on one to get it to look like the other one, right? I mean, just for the very fact that there's 3 terms in the denominator of the second one. That doesn't look like the first one. That looks distinctly different, right? Okay, so this is an example where, especially in this particular section, checking the back of the book and saying, I'm wrong because my answer doesn't match theirs, might not be your best choice. Okay, just because their answer doesn't look like yours doesn't necessarily mean, I mean, you still may be wrong. That's still a possibility, but you might also not be. Because the answers can really look very, very different from one another and both be correct. Which means grading is exceptionally difficult for this because I have to very carefully follow what you did and make sure that you followed a pattern that actually worked. Okay? Any questions on this one? All right.